All right, guys, welcome back. So last time we talked about some of the issues regarding supervised learning in the context of big data. So, having a large data set makes everything difficult, right? That was the takeaway message from the last class, right? So even a simple model like a linear regression model, when you try to compute the pseudo inverse, there is an issue. In case you have a large n, then you may not be able to compute the pseudo inverse in a efficiently. And when n is really large, then you are not going to be even able to fit that pseudo inverse matrix into a RAM. So what that means is with a single computer, you will not be able to compute the pseudo inverse, and therefore you will not be able to train your linear regression model. And if you cannot solve your problem with a linear regression model, then more complicated model is going to have even greater issue. So that was the problem that we looked into last time. And then we actually have seen some strategies in order to get around those issues, including, sitting down and cry and wait, right? And I indeed have emphasized that, taking time to think about a problem actually helps a lot. And then, we also take a look into the technique of using some algebraic tricks, right? So last time when we compute the pseudo inverse, we saw the trick of changing the order of computation. And then in that way, we could see that there we go. In that way, we could see that the result of computation was dramatically different, right? So computing everything in the order of what is written in the formula versus slightly changing the order of computation in such a way that you compute the x transpose x inverse first, and then compute the x transpose r, and then multiply them together. And it sounded like a very simple trick, but it resulted in a great deal of difference. Okay, so regarding that, I would like to discuss today two more things. One is we're going to talk about distributed optimization algorithms, which is quite common in big data services, including Spark. And then we're going to move on to how to implement all this kind of things in Spark machine learning library. So primarily, we're going to use Google Colab for today's lecture. But before that, let me try to share a whiteboard because I want to explain something before to get into the fun programming exercise. So here's a whiteboard. I hope this is, you can view this well. Let me see. So just as a brief recap of what you've already learned from an undergraduate level calculus class, you probably heard about this thing called the gradient, okay? So gradient is defined as something like this. So this is, of course, when you have a three-dimensional coordinate system spanned by the x-axis, y-axis, and z-axis, right? And then the definition of the gradient of a function was simply partial f, partial x, partial f, partial y, partial f, partial z, okay? So what's the meaning of that? Okay. So before to talk about the meaning, let me actually simplify it to a two-dimensional space. So we're going to talk about only x dimension and the y dimension, okay? So function f, in fact, if you visualize it, it is a map defined on this xy dimensional space, okay? And each location at this xy dimensional space, we have a function value. And then depending on the magnitude of the value, I'm going to use a different color to indicate their value distribution. So red means, higher value, green means 0, and then blue means maybe, some negative value. So you can imagine, a value is distributed across this, two-dimensional space spanned by x and y. Now, if you think about the geometric meaning of the gradient, okay, what does this mean? So let's try to understand. Let's try to interpret what it means by partial f, partial x. So in plain English, partial f, partial x means the change of the function value f with respect to the change of x, right? So when you move from one, let's consider this black dot in the middle of this red circle, okay? So what the gradient means is when you move toward the x direction by an infinitesimal amount, what is the change that you experience in terms of the function value f? So in case of this point over here, as you move to the right to the x direction, the function value is going to decrease from red to orange, right? So we're going to have some negative negative value for partial f, partial x. Same thing with partial f, partial y. So consider the same point. As you move an infinitesimal amount in the y direction, then again, the function value is going to decrease by a little, right? And the function value is going to decrease from red to orange, right? Now, depending on where you begin with, the gradient value is going to be different. So in this new case, so this is the second point over here, if you move toward the right by an infinitesimal amount, you will probably experience an increase of the function value. Same thing with the y value, I guess, right? So as you move toward the upward direction, the function value is going to change, going to increase by a little bit. So that's the meaning of the components of the gradient. Now, what does it mean as a whole? What is the meaning of the gradient as a whole? There was, in the meantime, in the chat window, a question asking to explain the color codes again. The color codes are basically just a graphical representation of the function value. Red means a high value, blue means a smaller value, okay? And I'm just, assuming a hypothetical function. So that's the meaning of the color code, okay? So Daniel actually brought up a great point. So the geometric meaning of the gradient, okay, the conclusion first. The meaning of the gradient is the direction of the steepest increase of the function value, okay? Why is that? Because what partial f, partial x is going to give us is the increase of the function value with respect to the infinitesimal change in the x direction, right? So how much of increase do we see, right, in terms of the function value? Same thing, partial f, partial y gave us the change of function value with respect to the infinitesimal change in the y direction. So again, the function value is going to either increase or decrease or maybe stay still, right, as you move by an infinitesimal amount to the y direction. And then there's going to be a change. And partial f, partial y is basically describing how much the value changes. And if you think about it, okay, the vector gradient, first of all, is a vector. Again, it becomes a little too crowded, but it's a vector whose components are partial f, partial x, and partial f, partial y. So you can think of it as a vector, in fact. That's the definition of the gradient. So if you think about it, the gradient is the direction of the steepest increase of the function value. And then when we decompose that into x directional component and the y directional component, okay, each of them are going to be partial f, partial x, and partial f, partial y, okay? So without knowing the equation of this color-coded function, I can actually tell the direction of the gradient, okay? For example, let's say I'm here, okay? If I'm here, the direction of the gradient is going to be this direction. Because again, the gradient is a vector indicating the direction of the steepest increase of the function value. So in other words, which direction out of this whole 360 degree, which direction do I have to move to make the function value increase the most? Okay. So similarly, if I'm over here, the gradient direction, without knowing the function, the equation of the function, the gradient direction is here. Okay. So the reason why I'm explaining this is because of the optimization problem that we discussed last time. So you have a target value y, and then you have some machine learning model f, which takes in a feature vector x, and you want to minimize the difference between the two. Okay, so that is what is called an objective function or a loss function. And the role of the loss function here, what we're trying to find the function f. Okay, that's the unknown here. We're trying to find a function f that minimizes this equation over here. Now, in the linear regression problem, fx is parameterized by w and b. Oops. So it's xw plus b. That's the That's the linear regression model. So in other words, we want to find the parameter W and B that minimizes y minus xw minus b squared. So that's an optimization problem. So one solution to this, which is the one that we saw last time, was to solve a linear equation and then find the pseudo inverse. So with a slight abuse of notation here, the optimal W was determined to be the pseudo inverse times the response variable, right? So that was basically how we computed the optimal value W. But the problem with this was that we needed to compute this large matrix in case when the number of data samples is large, then the matrices are going to be really big, and therefore it is really difficult to compute this in a single machine. So today we're going to explore an alternative where instead of computing this directly, we can iteratively update. And then even better is, not only iteratively update, we're going to actually distribute the task into parallel machines. Okay, and the strategy is, in fact, we're gonna leverage the fact that the gradient, okay, is always pointing toward the direction that the function value increases. So in other words, if I compute the gradient of L, the loss function, this vector is going to give me the direction where I can increase the value of this. And that's actually the opposite direction that we're looking for. We want to decrease the value. So what I'm going to do is simply put a minus sign. Okay. Now, my strategy here is basically to update W, okay, each time by moving W along the direction of the gradient with a step length alpha. So again, we have a space defined by W. So if I simplify, then we're going to have W1, W2. Of course, it's going to be much higher dimension, right? A dimension of D, but let's simplify it into two dimension. Let's assume that we have only two parameters, W1 and W2, okay? And then the loss function is defined as a function on this space, right? So I have this color-coded function over here. And what I'd like to do is I'm going to initialize W with some random value. So I'm going to start with some, random location. And what I'm going to do is, well, I'm going to, first of all, evaluate the direction of the gradient, okay? And then I'm going to take a negative value of that, which means I'm going to take the opposite direction of the gradient, okay? So remember, gradient is the direction where you're expected to increase the function values the most. If you take the opposite, then it's going to be the direction where you're expected to decrease the function value the most. And then I'm not going to take the full length of the gradient because I'm, let's say, conservative. I don't want to make a too large step toward the direction. Instead, I want to deduct it by, some factor, alpha. So alpha is what is called a step length. You can decide to go the full stride toward the gradient direction, or you can decide to go by half stride toward the gradient direction, or you can decide to go by twice big as your stride size. It's a parameter that determines how aggressive or how conservative you want to go in the gradient direction. So that's the constant alpha. That's a scalar constant alpha. And what I'm going to do is I'm going to update my current W, which is the point over here, by moving toward that gradient direction. And that's going to be my solution at the next iteration. And then I'm going to repeat that process by following the step toward the gradient. And here's an important thing. Gradient is the direction where I expect it to decrease the function value. So if I follow the direction of the negative of the gradient, eventually I will be converging towards a minimum value where I cannot decrease the function value anymore, and therefore the gradient is 0. Okay? So long story short, too long didn't read. The long story short, what we're going to do is we're going to update the weight value W by keep evaluating, first of all, the gradient of the loss function. Well, let me be a little more specific. By evaluating the loss function with respect to the value W at the current location W. Oops, I should have be consistent. So it's actually L, right? And then each time I have a step length defined as alpha, okay? I'm gonna repeat this until the gradient value is bigger than 0. Sorry, the magnitude of gradient is bigger than 0. Okay. And as a result of that, I'm going to converge to a minimum, okay, where I cannot further decrease the loss function value anymore. So that is what is called a gradient descent. Yeah, with that, I'm going to move to the Colab, and instead of talking too much, I'm going to show you how exactly that's done, okay? So like what we did last time, what we're going to do is to create some synthetic data, okay? So don't be disappointed. We're going to play with some virtual data at the moment, okay? So let's be actually a little more ambitious. Let's say we have 1 million data points, okay? Because this is a big data class, right? We got to go big. So we have 1 million data points, and then let's say we have 10 variables, 10 columns in our data. So the feature matrix is going to be, well, I forgot to actually import NumPy, sorry. Import NumPy as NP. So the feature matrix is going to be a random matrix that I create. The random values will follow the distribution of Gaussian distribution with an average of 0, and then the standard deviation of 1. And then the size of the feature matrix is going to be obviously n by d. And then the response variable is going to be, again, another random matrix. I'm going to just set the same condition. And then the size of the response variable is n by 1. So we have n observations, okay? And each observation is represented by a feature of dimension 10, okay? That's what's going on here. So let's run that. Now, after that, well, first of all, let's begin with the gradient descent algorithm. Okay, so to make it easier to kind of track down what we just discussed, we have the function, and you don't have to type this. I'm just putting it up here to make it easier for you guys to memorize. So the function f is what? Is x times w plus b. Okay, or to make it a little more specific, we have total 10 dimensions. So that's going to be x1 times w1 plus x2 times w2. And then dot, 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 x and x10 times w10. Yep, h dots. I thought it was c dots. Well, whatever. I meant to type dot, dot, dot. I thought that was c dots. So this is the linear model, right? So we have total 10 dimension, x1 through x10, and then plus b, which is the intercept. So, and then the loss function is what? The loss function is, well, it's a function of w. So I'm gonna just, you know, I'm lazy. I'm just going to put that as wb. So the loss function is a function of w and b, and then what we're trying to do is to, you know, minimize the discrepancy between the prediction of the model and the actual ground truth value. And then when we do that, we want to do it for all the data samples that we have in the data set. So let's say we have the superscript t indicating the data point, the tth data point, and we have to take the summation from t equals to 1 to n. Okay. So if you have absolutely no idea how I'm, you know, typing this equation, it's a thing called LaTeX. You don't need to worry about it. Just focus on the equation on the right. Okay. So this is the loss function that we're interested in minimizing, and to make it a little numerically more stable, let me divide it by the total number of data point n. Okay, so that's going to be 1 over n multiplied in front of the sigma. Okay, so this is essentially something that we're trying to minimize. So in order to do that, let me first of all define the variable w and the variable b. So and then the gradient descent idea was to begin with some randomly initialized parameter. So what I'm going to do is simply just create a uniform random variable that's setting between -1 and +1. So I'm just picking some random value between -1 and +1. And then the size of the matrix W is going to be d by 1, right? And then B is a scalar. So again, I'm going to just pick a random scalar in between -1 and +1. Now, what I'm going to do is I'm going to go over a for loop. So I'm going to define an iteration. So let's first of all define maximum number of iteration, because we don't want the iteration to run forever. So let's say I have maximum iteration of 1,000 times. Now, what I'm going to do is to then compute the gradient. So partial L, partial W, so Dldw, that's the gradient. So gradient of the loss function with respect to the vector W. And then I will need to compute Dldb, because B is another variable. Okay, excuse me. And at the end of the day, here's how I update the model. And that's going to be just to update the value W by some learning rate multiplied by Dldw, and then B is some learning rate multiplied Dldb. Okay, so this is a basic structure of the gradient descent. Of course, I have to define learning rate, and for now, let's just call it 0.01. It should be fine because it's a linear model. So these two are the user-defined parameters. Okay, so now we simply need to compute the Dldw and Dldb. Okay, and then this is going to give us, the optimal W and B for a given data set, specified over here. So how do we compute the Dldw? Well, you've already taken calculus, so it's actually not that difficult because we're talking about a linear equation. So partial L, partial W, okay, is defined as what? We have a linear equation, and then we're taking the derivative with respect to W and B, right? So let's actually make it a little more simple, okay? And let me back up a little bit and then explain to you a trick. So I'm going to actually introduce this this term called the L sub t, L superscript t, okay? And then I'm going to define that as just this portion without the sigma, okay? So by this definition, okay, what happens now is Lwb is simply just the summation of what? L superscript t. So what I'm doing is essentially just what's inside of the summation symbol, okay? I'm going to represent that as Lt. That's basically what it is. And at the end of the day, the loss function as a whole is going to be a simple summation of those t terms. Okay, so with that annotation, let's make the gradient a little more simple. So instead of taking the gradient of the entire thing, let's take the gradient of a single term. And that's going to be the derivative of this line over here. You see that? So we have a square. So we learn from calculus. If you have a square of the exponent, just put it down, drag it down, and put it in front. Okay. And then what? We need to take the derivative of f with respect to w. And that is going to be simply x of t. Because it's a linear equation, right? W and x are linearly combined. So if you take the derivative of the function f with respect to w, you're going to simply have xt. Okay. Same thing. Derivative with respect to b is even simpler. So derivative with respect to b is, again, 2 comes in front, and then you have the same thing within the parentheses, multiply by the derivative of f with respect to b. Derivative of f with respect to b, which is just 1, right? So in case of the gradient of L with respect to b is just this equation over here, okay? So if you don't get what it is, I'm pretty sure you'll be able to brush up a little bit by, go back and, grab a calculus book, and, you'll be able to kind of remember what you learned from calculus. I'm not going to go any deeper into how to actually calculate the gradient because I assume that you learned that from a math class, okay? So these are the gradients. So what I'm going to do is then, for convenience, I'm gonna, well, actually, I forgot to put 1 over n. So that's gonna be actually 2 over n. Sorry for that. Okay, so that's the gradient. Now, I'm gonna just write this down, okay? And to make it a little simple, what I'm going to do is, compute this first, and then I'm gonna define Dldw and Dldb. So in fact, y minus f is what is called a residual or error, right? So what you want to do is basically to take the difference between take the difference between y and f, okay? And that's exactly what you want to do. And then Dldw is going to be ERR times x, right? I'm not following the syntax at the moment. I'm just sketching the idea. So, and then, Dldb is going to be this, okay? Again, this is not the exact syntax. We're going to refine it. But to sketch the idea, this is basically what's going on. And I just realized that I forgot to put the negative sign, right? I think I need to put that in the both sides. So it's going to be like this, okay? So then, well, maybe just simply flip f and y, okay? Now, let's think about it. Y is an n by 1 matrix. Actually, I should have used a capital Y. And then what is f? F is, in fact what? X multiplied by W, and then that's a matrix multiplication. So we got to use actually matrix multiplication of X with W, and then plus B, right? So that's essentially our equation. So that's how we define f. And then the error is f minus y, okay? And then 2 over n is a scalar. And the error is a matrix. And x is also a matrix. So you need to actually do the matrix multiplication between, well, no, it's actually not, right? Yeah, sorry. It's actually not a matrix multiplication. It's just a multiplication of error and x, and then Dldb is like this, okay? And then in fact, this formula over here was for one term, and then we have to take the summation over the entire data points, right? So that's going to be np dot sum of this in the axis of 0. And then for the simplicity later, we're going to keep the dimension true. Same thing. We're going to take the summation of this along the axis 0. Axis 0 is, we have n by d. So this is the first axis, and this is the second axis. So we're taking the summation along the first axis. Zero's axis, right? So that's why we're putting axis equals to 0. And then we need to keep the dimensions for simplicity in the later. Okay. So I guess that's it. So since I want to monitor the progress, maybe, I don't know, let's let's print W. And I don't want it to be too crowded, so let's print it only when every 10 iteration. So every 10 other iteration, I'm gonna print, let's just print B, because W is a vector, so I'm worried that things are gonna be too crowded. Okay, there you go, sorry. X, large case, yes. Yep, is it already? Sorry about that. I should have taken a transpose because W is 10 by 1 and Dldw ended up 1 by 10. So I'm taking the transpose of it. I don't think I need it for B though. Yeah, there you go. So as you can see, the value of B is evolving as the iteration goes. And then it will become something, okay? Of course, I don't know the ground truth because it's a random matrix. It's a random data. So I don't know if this has converged to an actual value or not, but there's a way to check that later because we know the pseudo inverse thing. Okay? So over thousands of iteration, you can see that B is converging to some value. So initially the B was changing quite rapidly. Now the speed of changing is really slow because that's because we're closer to the gradient. Okay, and as you can see, it is converging toward somewhere around 0.0018, right? So here is, I'm going to stop this. Here's one additional technique that I'm going to add, which is if Dldb and np dot absolute value of that is smaller than 0.00006, sorry, 01, then we're going to just terminate the iteration, okay? Because anything smaller than this number, it's not very significant, right? So in that way, you can implement your own gradient descent algorithm in NumPy, okay? So if you're not a computer science major, this might have been a little, I don't know, difficult to digest, but that's all right. This is not the eventual method that we're going to use in the class. Eventually, you'll see that this all boiled down to just 1 or 2 sentences in Spark language. So you don't have to worry too much about it, but I hope this is a good example that shows how the gradient descent works inside a computer, okay? Any questions so far? If you have any question, I'm monitoring the chat box, so feel free to drop the questions over there. Okay. Well, in fact, I did not open the chat window. Sorry. All right. So that's that. Of course, if you want, last time we talked about computing X transpose X and then computing X transpose Y and then multiply them together to get the ground truth. So you can actually do this operation and then compare the solution that you obtained from the gradient descent with the solution that you obtained using pseudo inverse and see if they agree with each other, okay? But in today's class, I'll just trust my implementation because I'm pretty sure this implementation is correct. So if you're interested, try to implement that and then try to compare it with the WMB that you obtained from the gradient descent and the WMB you obtained from the pseudo inverse, and they're going to be the same. So that's basically what the gradient descent is. Now, this is not actually what we're interested in doing. We have to go one step further. In the big data systems, even this is going to be quite painful. Let's try to measure the time that's required for each iteration, okay? So last time I showed you how to measure computational time, right? So time.time was the function that you're looking for. So at the beginning of the iteration, and then at the end of the iteration, I'm going to just print the time for each iteration. So time.time minus start time. That's going to give the time that is elapsed for running this portion of the code, right? And then maybe let's set the max iteration to 10 because we're interested only the computational time, not the final solution. So as you can see, it takes about 0.1 second. Okay. And again, it doesn't sound like a lot of computational time, considering that we're using 1 million data points, right? But don't be satisfied because there's a better way, right? And also, remember that we're using only 10-dimensional feature. In case we have something bigger than this, then obviously the computational time for this is going to go up, and you don't probably want to spend that much of time. Yeah, and in fact, this is for one iteration. So even if one iteration takes only 0.1 second, if you multiply that by 1,000, which used to be our maximum number of iteration, it can be quite painful to wait for the computation to be done. So the idea now is to distribute the data into multiple nodes. And as a matter of fact, we talked about Hadoop at the beginning of the semester. And then the key point of Hadoop distributed file system is that you break a file into different blocks, and then you distribute that block across different data nodes. And in fact, if you think about it, the big data system by its nature, you don't have all the data in one single machine. Rather, what you're going to have is, in fact, a situation like this, where you have now, let's say you have 2 data nodes, okay? So node 1 has, let's say, 500,000 data points, and then node 2 has the remainder 500,000 of data points. So that's going to be n minus n node 1, right? So let's say you have 2 data nodes, and then you're distributing the the original 1 million data rows into 500,000 and 500,000. Okay, does that make sense? So then each of the nodes, so node 1 will have x, right, and y, and then node 2 will have x and y. Okay, of course I could go with the larger number of nodes, just than just 2. But for simplicity, let's just consider 2 nodes, okay? So then let's say the first 500,000 rows are in node 1, and that's in Python syntax like this, okay? And then, same thing for y. And then the remainder of another 500,000, which is going to be from n node 1 to all the way through the end, is going to be sitting in the second node. Okay, does this make sense? So simply speaking, imagine you have a data table. You split that into half. You count the first 500,000 rows, and then put that into a node 1, and then you cut the next 500,000 rows, and then put that into the node 2. And this is going to be that distribution of the original data set. Okay. Now, how do we solve this gradient descent algorithm? Again, now let's think about the gradient descent. What should we do? Well, the good thing about this gradient descent algorithm, that our formulation here, okay? The good thing about this formulation is, in fact, we define the gradient per each data point. You see that? So we computed the gradient per each data point, and then the global gradient was simply the summation of the individual gradient. So what I mean by that is, okay, gradient operators are linear. So what that means is, if you take the gradient of the entire thing, it is actually essentially going to be same as the summation of the individual gradients. So, oops, did I do something wrong? Oh yeah, sorry. That is this line. I forgot the partial, right? So this line. So I repeat it again. The global gradient, the gradient of the entire loss function, is simply going to be the summation of the gradient of the individual terms. So what it means is you visit each of the row, compute the gradient, okay, for each of the row, and then at the end of the day, you just take the summation. So if you think about it, this is beautiful because we have just split the data set into 2 chunks, one for node 1 and then the other for node 2, what you need to do in order to compute the gradient of the entire loss function is simply to visit each of the node, compute the gradient, and then after that, we just take the summation of it. Okay? So what that means is, here's the trick. So I'm going to get rid of the portion where we computed the gradient in the previous example. And then I am going to, actually I should have done this, and then I don't think I need to measure time anymore. Okay, so I technically erased the first few lines over here. So what we're going to do is, okay, here's node 1. Okay, so master node talks to node 1 and asks for gradients. And what I mean by that is local gradients. And then the node 1 responds, hey, yes, okay, sure. So f of node 1 is going to be then np.matmul x node 1 multiplied by w plus b. And then error at node 1 is f node 1 minus the ground truth at node 1. And Dldw, which is the gradient at node 1, is going to be np.sum 2 over n times error at node 1 times x at node 1. And then similar to before, we're going to keep the dimension true. And then same thing for Dldb at node 1. And that's going to be without this x node 1 here. Everything is the same. So that's what the node 1 does. Okay. Of course, in this Colab environment, I cannot show you, I cannot physically split the data nodes. But you can imagine that this is being computed in the node 1. And then to be more specific, when I say master node talks to the node 1, I meant master node sends W and B to node 1. Okay, and then the node 1 computes these 4 lines and then return Dldw and Dldb back to the master node. Okay, now similarly and simultaneously, master node sends WB to node 2 this time and asks for local gradients. And the node 2 is going to do essentially the same thing. Okay, so I'm just going to reuse the code and then just change the node index from 1 to 2, because node 2 is going to do essentially the same thing. So far so good. Now the result of that is going to be sent back to the master node. So this is what then the aggregation happens. Node 1 and node 2 sends back to master node both Dldw and Dldb. Okay, and again, since we're just simulating that situation, we already have Dldw and Dldb in the master node. So then what the master node does, aggregates the local gradients and produce the global gradient. And that is simply, we saw that, the summation, right? So to be more specific, you can think of it as summation from 1 to 500,000 plus I guess I'm insulting you. This is pretty obvious, but I just wanted to make it crystal clear what's happening over here. Okay, you see this? So the summation could be split into the part for node 1 and the part for node 2. So we simply need to just take the summation of the Dldw and Dldb. So the global gradient is going to be the summation of Dldw node 1 plus Dldw node 2. And similarly for Dldb, it's going to be Dldb node 1 plus Dldb node 2. And then master node updates the model. And then, if the Dldb goes below this, then we break out of the for loop. Otherwise, we go back to the beginning of the for loop. Master node again sends WMB to node 1 and then asks for local gradient. And then the node 1 is going to compute the local gradient. Node 2 here is going to do the same thing simultaneously in parallel, right? And then at the end, we're going to aggregate the Dldb and Dldw, and then we update WMB. And then again, check the convergence. If not, we go back and repeat the same thing. And again, let me emphasize this again. What's happening in node 1 is not dependent of what's happening in node 2, right? Are we referring anything? I don't think so. So the computation that's happening in node 1 can be completely independent of the computation that's happening in node 2, and therefore we can make it parallel. Of course, again, we assume that we have only 2 nodes, but if you go to a big data cluster, there's going to be thousands of nodes. So now imagine, instead of splitting 1 million data points into 2 nodes, now imagine you're splitting 1 million data points into 1,000 nodes. Still the same thing, except now that each of the nodes needs to handle only 1,000 data samples as opposed to 500,000. But the rest of the calculation is going to be exactly the same. And unfortunately, we have only 4 minutes, so I'm going to give you a teaser of what we can do. And then in the next class, I think it's next Tuesday, we're going to continue to talk about it. But to give you just a gist, we last time saw, how to read a CSV file. That was basically just a file name here, right? And then it created a data frame for Spark. And then in Spark, what we have is this thing called a ML library. So PySpark.ml. It used to be called the MLlib, but with the newest version of Spark, they no longer call it an MLlib. ML is the name of the module that is in the modern version of Spark. So if you actually Google Spark machine learning examples, you probably find quite a bit of examples that comes with something like this. And that's because, that's from the previous version. So with the brand new version, this is how things are done. And then, what we're going to do, again, this is just a kind of a teaser of what we're going to do tomorrow, not tomorrow, next Tuesday. We're going to convert the data frame into feature vector using what is called a vector assembler. Okay, and the vector assembler is basically to define what are the columns that we're going to use as X and what are the columns that we're going to use as Y. Okay, what is the independent variable and what is the response variable? So that's defined by vector assembler, and then we're going to put some options there, and then just transform. And then that will transform the data frame into a feature vector, and then easy enough. The next step is going to be to import machine learning library, especially regression module, especially linear regression function. Okay, and our linear regression model is going to be linear regression and features something, 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 and the labels something, something, something. Okay, this is not the exact syntax, but just to explain to you conceptually. And then finally, the model trained as a result of linear regression can be computed as this. Okay, so that's it. This is essentially what it is. So I typed what? How many lines? I loaded the CSV file and vector transform, defined the linear regression model, and then fit. It's only 4 lines. Okay, and then inside of this dot fit, there is actually an implementation of all this, of course, in a much more sophisticated version. Okay, that can handle all the exceptions, allocate the data nodes and computing nodes and everything. So all of that is all of those heavy lifting is going to be taken care by Spark machine learning library. So from a data science perspective, you just need these 4 lines. That's it. Okay. So remember the meme that I showed you on Tuesday, right? When advertising, it's a distributed computing. when hiring, it's Spark, and when we're using it, it's a SQL, and that's exactly what it is, right? Distributed computing and all this kind of thing. The things that we learned from the theory class, it sounded really complicated, but the nice thing about Spark is that all of that is kind of nicely integrated into like nicely integrated into behind the scene. And then as a user's perspective, you just need to know some basic syntax like this. Okay. Of course, there are a lot more to cover. Like we're gonna have to talk about the concept of the transformers and the evaluators. And then we're going to need to talk about how the tasks are distributed and so on and so forth. Those kind of things we're going to continue on Tuesday. So thank you guys very much. Appreciate it. And I'll see you guys next week.